embeddings are our next two rock stars. And this one's it's called Making Use of All Your Data, labeled or otherwise. Jessie Wang, Brad Nguyen. Now I'm going to classify these two as hard-working touring musicians on our great concert today. They are polished by long experience in the field. And like a great touring band, the sum of the two is even greater than the individuals. And I'm going to, and everyone's going to be, all you millennials are going to be rushing to Google, because I'm going to compare you two to the Eurythmics. Now, the Eurythmics was a great band from my era. And actually, you know what, I think we might sneakily, Fiona, if you'll forgive me, give away a book to who on the channel in this Talks channel can tell me which Australian town the Eurythmics were founded in. That's a really obscure piece of music trivia. First up to get that will win the book. Brad is a senior consultant here at Thoughtworks. Recent experiences included data strategy advisory work. He has got the hottest letters in town, CD for ML. So continuous delivery for machine learning. Oof, that is so hot right now. Does that kind of work. Chatbot building, machine learning proofs of concept. That's a very, very sexy sort of a resume. Pockets of experience in other old technologies like web apps, microservices and app development, DevOps. Oof, so last Thursday. But prior to Thoughtworks, he earned his stripes as a game developer for EA Games, data science role, all sorts of places, Sportsbet, Redbubble, amazing. Jessie, a talented data consultant at Thoughtworks here, another person in hot demand. Passionate about optimization and operational research. So making it real, machine learning, all those areas. She's been both an academic and an industry assistant researcher at the University of Melbourne, and solving real world problems for the local council, bottlenecks of transport. Well, they're not out there at the moment, Jessie, so we're pretty glad to have you instead. Worked for all sorts of our clients. They've been wonderfully lucky to have you. And today you're going to talk about supervised learning, the problem starting with a labeled data set. So even I know what that's about. It's like data comes in all shapes and sizes. I think Matt Kelsey on our podcast, Press 2, talked about poor old data engineers and scientists are probably going to spend at least half their time just looking for the data, let alone whether it's well sorted and well labeled. So I'm going to let you talk about that today. You're both experts in it. Thank you so much for coming. And we'll see everyone else over in the channel.
Thank you, Nigel, for the introduction. As Nigel mentioned, Brad and I will talk about how to make use of all your data, no matter it is labeled or otherwise. So before we go to introduction, I want to be clear that in order to 100% understand the context, you may need some simple background in machine learning. And you may be familiar with terms like loss function and label. So now we will talk about our motivations. There are 3 reasons motivate us to do this talk, and they're all based on our previous experience. So in our previous work, we normally have a very large amount of unlabeled data, but only have a little bit of labeled data. And if we build a model only based on this label data, and then it's kind of like a waste of the unlabeled data. So it raises a question like, can we make use of both limited data and unlabeled data to build a machine learning model that is actually functional and working pretty well? Oops. And yeah, and then the second motivation is linked back to the label data. We want to reduce annotations time. So because every label data, we need human to actually label them. And this involves label cost. So it's a way to reduce annotation time, as in the same amount of time, we can label more data. Or we always label the more important data point first. And then the lastly is when we're working with different clients, things change rapidly. They always have new products onboarding. Is a way the model can quickly recognize a new product and then digest it, and then in the future we can actually use the model to recognize them. So that's the 3 motivations we have. Now I will pass to Brad to talk about our approaches.
Yep. Thank you, Jessie. Here, I would like to give a very quick, quick explain a very high-level overview of the whole landscape of machine learning, so we can follow this talk. So if we start from the top row there, this is the where traditionally people look at in machine learning, where you look at supervised learning. So that's the case where you have all the data and you tell the model what to expect to classify or predict. So that's the case where you have the labels. And if you look at the other extreme of it, if you look into unsupervised learning, so that's the bottom row there, where you only have the data, you don't have any labels, right? So in that case, normally people can only do either anomaly detection or you can group together similar things. That's the only thing you could do. So, but if you pay attention to the middle area there, is what we think we often see a lot in the real world. So in fact, that's probably the most common in the real world, where you have very limited label data. Just a few label data, because we know labeling data is quite a human-intensive process. And you have lots of unlabeled data that you can also learn from. So what are the ways that we can actually combine the unlabeled data and then you add a little bit of labeled data to actually give you the same power as a supervised learning model? Yep. So for the next slide, I'm going to just very quickly introduce our running example for this talk, which we will use throughout the presentation. The data set we are going to demonstrate here is the fruit 360 data set. And they are really just that. They're really just a bunch of images of fruits. There are two parts of our talk. So in the first part, we are not going to use any label at all. So the only input we use are the raw images of those things. We don't even know the names of those things. So we only see the image of the fruit. In the second part, Jessie will talk about few shot learning, where she used a little bit of the label. So basically you also tell whether it's an apple or whether it's an orange, but with only few of them, and then the rest is still unlabeled. Right.
Yep, and now we at the start we want to tell you what we want to achieve. So here we want to at the end to build a classification model. And so if we put an image into the model can see what's this image. So in the first example, if we put a green round-ish thing into model, and then the model will say, haha, it's an apple. And if we put a red sparkly-ish thing into the model, and then the model may say, it's not an apple. So that's what we want to achieve at the end.
Right. So that's the goal that we want to achieve. And so how do we get there? So in this case, I'm going to give a overview of how our talk is structured so you can follow. So it's divided into two parts. In part one, we are talking about this thing called representation learning, which is totally unsupervised. So we do not use any labels at all. We just look at a bunch of raw images, and we want to train a thing called embeddings model. So this is really just a way to represent things. And in the second bit, we talk about few shot learning, where you use that embeddings model and then you can apply to train a downstream model, which in this case is the apples versus non-apple, or apples versus lychee that Jessie mentioned. So that's an overview. Right, so next, I'm going to go into a little bit of detail now to talk about representation learning. So just to recall, so the goal of this step is to be able to learn to represent different things, right? And it's an unsupervised learning, so we do not use any labels at all. The only input that we receive is just a bunch of raw images of those things. I wouldn't know, whether this one is a banana or that one is a strawberry. I wouldn't know that information. I only know, these are a bunch of different fruits. And my goal is to be able to tell that if I see two bananas, I want to be able to know that these are the same thing. If I want to, if I'm shown a banana and a strawberry, then the model should tell me that these are two different things, right? And you may ask, like, how does it actually work? But if you look at the way that babies learn, for example, if you have babies in your family or in your extended family, right? That's actually how they learn things, because they can tell whether a cat is different from a dog without even before learning those words, right? Or if you show them another cat, they would probably know that it's still a cat without even know like the word cat. So that's not how they learn. You just look at the data first, and you try to derive some features to be able to represent them. So that's the goal of this step. So if babies can learn that, then the machine learning can also do that. We'll show you how. Right. So this is one example how you can train a model without telling it what it is, right? In this case, the input is an image of the banana. I wouldn't even tell it it's a banana, right? So you can, from that same banana, you can run it into two different augmentation functions. And it's really just a rotation of the image here. So that's one example. And we basically arrive at two data points now. So those are the two data points of the same object. Right? So if you feed them through to the same neural network, which is called encoder, and at the end of it, you try to ask the model to try to maximize the similarity, because they are really the same thing, right? So you try to keep the model to keep learning until they are really similar. Then what happens is, if you extract the last layer here before the projection, is what they call representation. So what's in this representation is really a set of feature that the model has learned that allow us to recognize that those two are really similar things. That could be the color, that could be the shape or the contour of the images that allows them to learn that these are really similar, right? So that's really just a pairwise way that you can learn unsupervised. So you have noticed that we haven't even tell them what it is, really just give them an image, right? That is one way to do it. Now, back to our fruit example, we probably can even do it better now. Not only we ask them to recognize similar things, we can also ask them to contrast things, right? I would like to introduce three notations here. So the anchor is could be any object. The positive is something really similar to the anchor. And in this case, you probably could guess that we probably just take the same anchor, we rotate them or we augment them just a little bit. That's a positive. And if you take a random selection outside of the anchor, you probably get something else entirely different. That's a negative, right? So the goal here is, now these three things is called a triplet. And it's one data point that we want to ask the model to learn that, well, I want you to try to learn that the two apples are really similar and the apple and the lychee is really different. Right. So in terms of a machine learning model, how would you do that? Right. The core concept of any machine learning model is a loss function. So if you have known machine learning, you would know that at the core is a loss function that the machine learning try to minimize. Right. So I'm just trying to pause for a very quick, just 2 seconds here, just so everyone can take a very quick look at the loss function. Right, and then just try to explain what it is. How do you write a function that the machine learning can really try to separate the lychee and the apple? So if you look at the notation, A stands for anchor, P stands for positive, and N stands for negative. So it's really just try to take the difference between it's an L2 norm of the distance between the positive to the anchor and the distance from the negative to the anchor. All right. So one way for me to understand this formula is, right, imagine that during the training of the model, so what we want to achieve is the distance of the negative should be a lot larger than the distance of the positive to the anchor, right? So if during the training, if for some reason the positive distance is still larger than the negative distance, if you look at the formula, what will happen is that subtraction is still greater than 0. So in that case, the loss is still can be minimized and the model still have to keep updating, right? if the distance of the negative and the positive is the same, then the formula will become the alpha, which is the margin here, right? In that case, it's still a positive term, so the model will still have to keep updating, right? And it only stops when the distance of the negative to the anchor is exactly greater than the distance of the positive to the anchor by an amount of alpha, right? So that's where it actually will stop. And that's when you can tell that the negative is actually separated by the positive distance by alpha. Right. Okay, so this thought, like, we wouldn't be able to go into a lot of details into this function, but so just play back the question out there for the audience. If you want to understand this really beautiful formula, if you want to understand more about it, think about the role of, for example, alpha. What happens if you remove alpha from this formula? What do you think will happen to the model? You can either try the experiment or run a thought experiment and let us know, what do you think is the role of that alpha here. So in the next case, we talk about this. Now, the quality of the model is as good as the quality of the data that you feed to the model, right? And how do we actually sample the data so we can train the model? In this case, we show you how we actually select the example that we can train the model. The columns, they are the data points to the model. So if you look at the first column, for example, that's really just one combination of the anchor, the positive and the negative. And the anchor and the positive, again, they are really variation of the same image. And the negative is something different else, right? Right. So a lot of work has been done on actually just how to select the data so to give the model the best shot of training and converging in faster time as possible. For example, if you just give it very obvious example, so that's very useful for the model at the start. But if you keep feeding it, very obvious example, it would not learn any new or useful information. So in that case, people have to really focus on the thing they call hard negative example. So those are really tight and very difficult to classify. And then the model can begin to pay attention more to how to better separate those examples. Right. So again, this is not the focus of this talk, but we just give you some overview of how people can actually do online mining of this sampling to train the model. Right. And at this point, we probably train a model without any labels. We get an embeddings. And a lot of people actually ask at this point is, how do we know if it's working? Because it's so abstract. It's not easy to see. Right? So one way is, remember that the embedding is in n-dimension space. So they are vector in n-dimension Euclidean space. Right? So one way you can do that is to project them down into 3 dimensions, which what we are doing in this case. The coordinates given in this visualization is given by the model, right? So, and the colors is the actual labels. So we cheat a little bit. We use the actual label here to send check the model to know whether it's working or not. So in this case, if you look at the visualization, you would see that like the thing with the same colors, they tend to group together. So the model is telling us that like based on the model, like things that are actually the same thing actually consider to be really close by the model. That's one way you can really sense check the embeddings. So next, I'm going to hand to Jessie. She will talk more about with the embeddings that we train, how do you actually take it further to train something else?
So now we will take a step further from embedding to a future learning. So we will start from high level concept. What is a future learning? So in a layman term, it's actually just a classification problem, but we have n different classes. And then in each class, we only have m labeled data. I haven't said that they may have many unlabeled data, but we only have m labeled data. So here is an example. We have 3 different classes, and each of the class, we only have 1 example. And then we'll use this to train a model. And then once the model is trained, if we give another input, and then the model will say, oh, this input is likely to be the first one, which is like an apple, green apple. And the feature learning is widely used in different areas. For example, here image classification is also used in segmentation and natural language processing. But in this talk, we will only focus on image classification. And just a quick recap. Brad already introduced what is embedding. Now just a quick recap. So in embedding, one way to train the embedding model is we randomly take 2 examples from our database. I take the first one as our anchor, and then we do some augmentation to create our positive example. So just emphasize that the anchor and positive are actually created from the same example. And then we take our second example as our negative. And if the model is well trained, then the model will map the image to an n-dimensional array. And then we can see this n-dimensional array as n different features. And if we plot these 3 n-dimensional array into a n-dimensional space, what we want to see? We want to see the distance between anchor and the positive is actually closer than the distance between anchor and negative. So that's embedding model. Then you may ask, what does embedding model to do with a feature learning? So one way is we can using the output of embedding model as features to train a classification model. So what I mean here is, if I have a image and I have a already trained embedding model, I put the image into the model and the model will output as a n-dimensional array. And then we use this n-dimensional array as n different features of this image to train a classification model. Basically is map this n-dimensional array or n features into a class. So why this is helpful? Because normally training an embedding model is a much heavier and complicated work compared to the classification model. Why? Because it involves a lot of parameters or weights. So for example here, this is already a super simple model for embedding, a super simple setup for embedding model, but it already have so much parameters. So each line of here can represent as 1 parameter or weights. And then compared to the classification model, we only have a few. And if we can make use of the embedding, take it as is, what do we need to adjust? We only need to adjust these parameters, which is a much simpler work. So it can save a lot of time and effort. And how does it work in the whole flow is we take image in. So this example is an apple, and then the embedding will map to n-dimensional array, and then classification model will take this n-dimensional array as input, map to a class, which is apple. And if we have a different instance, same process, embedding model take to n-dimensional array, and classification model and take the n-dimensional array to a class, which is not apple, this way. And then there is another way to do a feature learning is we still train a classification model end to end, but instead of starting from random parameters, we start from the parameters of embedding model. What do I mean is, so this square in this square, so this is the embedding, they have a lot of parameters. Normally, if we want to train a model from end to end, all these parameters is generally start from random. So it's random weights. But instead of from random, we can start from using the embedding model's parameters. Because it's already trained, so it's already have some idea about how the parameter should behave. So it means when we train end to end, it saves a lot of work. But this way, compared to the previous way we introduced, is still more heavier, more complicated, and more work to do. But the good part is, in this way, the output model will be more tightly fit into our specific problem. So in this way, if we have an apple, it will, instead of map to the n-dimensional array, it will directly map to the class, which is apple. And if we have a lychee, we take input into the end-to-end classification model, it will directly output to a not apple. So that's the two ways of doing a feature learning model. Now, as of now, we introduced some techniques about semi-supervised learning, and next we will talk about a little bit about machine learning of ops and operational constraints. So first, we want to link back to our motivation. One motivation we had, the first one was we want to make use of our limited data and unlabeled data, which you already done. We know how to make use of them and then build a good enough model. And then the second one is we want to reduce the annotator's time. How can we do that? Easy, because once we have a model already, instead of, as an annotator, instead of go through each individual unlabeled data point and then label them, what we can do is we take a bunch of unlabeled data and then put into the model. And then model will do some classification, say this is apple or not. And then we take all the apples and then show it to annotator at one go. Say, oh, these are all the apples classified by the machine. And then as an annotator, I was like, this one and this one does not look like apple. So I just circle them, say, these two are misclassified. So in this process, I actually labeled multiple examples at one go. So in other words, so in the same amount of time, I am able to, as an annotator, I'm able to label more data. So we can reduce our labeling cost.
Yep. So next I'm going to talk about some of the practical considerations that we reflect on when we did some actual project with in this area. So the first thing, like Jessie mentioned, MLOps is certainly one of the most, it's probably the most important things when you set up your ML project for success. So what we mean by that is, Jessie has mentioned that you need to iterate a lot on the data and the model. And the question we ask ourselves is, how do we make sure that we can do that as low cost as possible? So the fact that you can continuously develop, change the data, retrain the model again, get the metrics, and then monitor it, you should be able to go through that cycle in a matter of minutes, not hours or even days, right? So if you can set that to happen, then you have a lot of chance to iterate a lot more times on the model. It's not the focus of our talk as well, but there's another great talk coming up at 2:20 p.m. today by Hamid and Kiru. So if you would like to hear about MLOps, please head to that talk. And quite specific to unsupervised learning. So just want to raise some of the issue that we have seen. So what happens when you see like new unseen data, model drift, and those things probably will happen with any machine learning models anyway. But if you pay attention to our talk, they actually is probably more challenging in our case because there are two different components. So you got the embeddings that you train in an unsupervised manner, and you got the final classifier model that you want to train in a supervised manner. So how do we decouple two components? Because if you consider about, let's say if you have the classifier model has been deployed to hundreds of different operational stores. And now if you only update the embedding, you probably do not want to deploy everything again. That's probably a lot of downtime and a lot of cost involved in that, right? So in the same paper that introduced triplet loss, they also talk about things like harmonic embeddings. The fact that when you train an embeddings, you do not want to just do everything from scratch again, but rather, for example, you could mix some of the when you sample the data to train the model, you could reuse the embeddings from the previous embeddings, and you mix some example of that into the training, in that way, you got a better chance to have a compatible new embeddings, so you can still reuse the same classifier even with the new embeddings. So I think those are the few concerns that we think is quite important. And the other one is obviously how you do mining, whether you do like online mining or offline mining to select the sample to train the data. Where should we focus on the hard negative example or the semi-hard examples? Those are really important consideration to train either feature learning and representation learning.
Yeah, and so the last thing we want to say is iterative improving, as Brad mentioned. Now we can close the feedback loop. We have a healthy iterative improving cycle. So what we normally have in real life is we normally have some data asset, and then we want to have something in production. So in this case, we start with some limited data and a large amount of unlabeled data. We can build a model to recognize our product. Now, this model at the start may not be very good. It may not perform very well, but it's okay. We can still put it into production, maybe in a hidden way, so our customer will not see it, so it will not affect our customer experience. But if it's in production, it can start to generate more data, and then it will grow our data asset. So we will have more and more unlabeled data. And then if we use the smart annotators way to label more data, it means our label data set will also grow. Once we have more unlabeled data, more label data, that means our model will have better performance. So our performance is improving as well. So in this way, once when we go through this cycle multiple times, our model is in a good shape. We will be happy to release it and actually be customer facing. Now, as think of example, like if we are working for a supermarket, our model can recognize all the existing items like banana, apple, orange. And then one day, the creative farmer, they have a diamond fruit come up. And then of course, this diamond fruit, the model never seen it before. They don't know what is diamond fruit. So what the model will do, maybe the model will classify it as a item I don't know. And now as an annotator, what I do is, in a regular basis, I can check the class I don't know to see is there any new stuff. And then if I notice the diamond fruit, I say, oh, this diamond fruit is a new product. So I will label them. I will find all diamond fruit and then label them. And then so that our model will also quickly recognize what is a diamond fruit. This means we can faster onboarding new classes. So now our cycle can healthily keep improving and then digesting more and more different products.
So that brings us to the summary. Here we just would like to come up with some really high-level takeaways for you. So what we have demonstrated here is really how you can train a model with very little label data. Because if you pay attention to the way that we sample the data, there's no label at all. We really just take the same apple and randomly pick another lychee and then train how to separate them. So that's how you do that with very little label data. And that's the first summary.
And then we also introduced what is semi-supervised learning. We introduced some techniques like official learning, and then we also introduced the embedding models. So as of now, we are more equipped and more comfortable with working with unlabeled data and a little labeled data.
Right. And the final thing is we cover a number of operational concerns, ML ops. How do you ensure that you can train embeddings successfully? How do you visualize them? Those things will hopefully give you a better experience the next time you're going to try with self-supervised learning. Yep.
Yes, thank you. So if you have any question, please feel free to ask. We will still stay online and then keep asking questions in Slack. We will be there. And if you want to find us, also you can find us on LinkedIn. Yes.
Thank you.
Thank you.
You sure can. I've put some of your contact details in the channel, so you might regret that, because I think judging by the activity in that channel, you are going to have a lot to look at later. There's a chance to look at it during the break and during the afternoon speaker, but we'll also remind everyone that we've put together a virtual speakers lounge for later in the day. And at the end of all the talks, everyone's going to pile into their channels, and a few of us are going to go into the hallway track and have a chat about how you thought it all went, who you enjoyed, all those kind of things. Now, I am going to pick a couple of questions out for you, so because there's no way you'll absorb that giant conversation, which I have to. You'll be pleased to know that Matt Kelsey pitched in with a giant rant about elements of machine learning. So you'll have to unpick all of Matt's work this afternoon. But gee, when you put up that triplet loss slide, you lost me. I think that's where those of us who are not technical fell out. I thought I was reminded sorely of the three-body problem, which I don't think was actually a solvable mathematical equation. And thank goodness we got you here to solve those sort of things. So I think a lot of people are interested in just the how, getting it done kind of thing. Ian G asked this question: what do you think of how machine learning algorithms analyze visual data versus simply text-based data, or even more complex, a combination of the two data types? Imagine trying to tease out the text of a document pictured in an image. So, and how do you, and in his experience, they've tried that a lot of times for work, and has found it very technologically complicated. Do you just buy a package? Do you just go to Amazon and get a subscription to Recognition? Do you start that from scratch? Are you overselling it, Brad and Jessie? Is it a really hard problem to solve?
Yep.
Who wants
Absolutely
to take that?
with you. Yes. Yep.
Is it Jessie? You want to have a crack at that one? Would you just buy a package to do a complex analysis, or how would you build something for that in the real world?
So in our work, we just did a simple example. We used TensorFlow, so built from scratch by Matt Kelsey and us. Yep. So it's not heavily relied on package. It's mainly start from scratch.
Brad, is it a solved problem? The mixed media problem of both pictures and image and words in the same documents?
Yeah, it is a well-known problem, I guess. And I guess the decision whether you buy or you build I think is a decision whether how much you want to iterate, improve, and customize your model, because there could be some nuances in your model that your recognition may be not really good at doing that. And I think there's already a lot of techniques out there in the self-supervised learning space. You can do pretext training. You can just try to take one part of the picture to train and predict it again, and you try to recover the text from the image. So a lot of techniques I think can be done. I think the advantage of when you build your own model is you probably can cover some of the nuances that is particular to your use case, I guess. And you can always compare to recognition from AWS as an incumbent. You could have a champion and a challenger model and see which one works better for you, I think. Yeah.
Well, we live in an amazing world with the availability of technologies and the whole cheap storage, cheap compute,
yep.
and image recognition as a service. It's truly, and thank you too for taking us to that future. We'll see you over in the channel, but it's time for a break at this point, and lots more information over there. I'll put all your extended references, etc., in the channel, and go and have a look and see what sort of controversy you've all created. Thank you so much.